In a previous video, we have learned about how the atomic orbitals of an atom combine with themselves to form hybrid orbitals. Also, in other videos, we learned that when the atomic orbitals from one atom overlap with the atomic orbitals of a different atom, they make the molecular orbitals of diatomic molecules. In this video, we'll build on that knowledge to understand how molecular orbitals are formed from the overlap of hybrid atomic orbitals in polyatomic molecules. Let's jump right in and start with an example. What is the correct Lewis structure of ethane, C2H6? That's right, the correct Lewis structure for C2H6 is this one. What is the hybridization of each of the central carbon atoms in ethane? Since the central carbon atoms have the steric number of 4, they have 4 things around them. Their valence orbitals will hybridize to form 4 sp3 hybrid orbitals. But what about the terminal hydrogen atoms? Normally, terminal atoms will adopt the same hybridization as the central atom to which they're attached. But that's only if they can. Since hydrogen's valence shell is n equals 1, it can't hybridize at all. So all of the hydrogen atom valence orbitals remain 1s. So as the atoms get closer to each other, the valence orbitals of the carbons hybridize. This is where we ended in our previous video. The question we now have to tackle is this. What will happen when we see these atomic orbitals and hybrid atomic orbitals get close enough to overlap? Let's zoom in on one of the overlaps, this one here, with the sp3 orbital of the carbon and the 1s orbital of the hydrogen. What is the result of the overlap between the sp3 of the carbon and the 1s of the hydrogen? As we saw with diatomic molecules, anytime 2 atomic orbitals overlap, we get 2 molecular orbitals. We get the bonding orbital as a result of the in-phase overlap, and we get the anti-bonding orbital as a result of the out-of-phase overlap. Here's one big difference with polyatomic molecules. No polyatomic molecule will ever have ground state anti-bonding electrons, so we're going to ignore them. But what should we call this new bonding MO? We don't need to invent a new name for this bonding MO, since we already have one that works. Since this is a cylindrically symmetric bonding orbital, we'll call it sigma. For the record, the anti-bonding MO that is made, but we're ignoring, is sigma star. Drawing these molecular orbitals can be a little tedious, so we'll use a much easier approach. Let's zoom back out to our whole molecule. Let's set up all of the overlaps. Each of these, the one between the carbon sp3 and the other carbon sp3, and all 6 of the overlaps between sp3s and hydrogen 1s orbitals, will make sigma molecular orbitals. These overlaps tell us that there's a sigma molecular orbital. We call a sketch like this, showing the valence atomic and hybrid atomic orbitals and their overlaps, the sigma framework. Time to finish things off for this molecule. How many valence electrons does the ethane molecule have? There are 14 valence electrons in ethane. Let's add them to our framework by drawing them as dots in the overlap. Drawing this dot tells us that there's one electron that will be a sigma bonding electron between this hydrogen and this carbon. Adding the second dot tells us that there's a second electron with the same wave properties as the first. What do the dots represent? Just remember, electrons are waves, and the dots are just a way of signaling that we have electrons behaving as these types of waves. Adding the last 12 electrons, we see that our molecular orbitals agree with our original Lewis structure. There are 7 pairs of sigma bonding electrons holding the molecule together. Of course, they aren't sticks or dots, they're waves. Let's explore a different example. What is the correct Lewis structure for formaldehyde, H2CO? That's right, in H2CO, carbon is the central atom, and it connects to the hydrogens with single bonds and to the oxygen with a double bond. What is the hybridization of the central carbon in H2CO? There are 3 things around the carbon, 3 atoms and no lone pairs, so its hybridization is sp2. What is the hybridization of the oxygen in H2CO? Remember that terminal atoms adopt the hybridization of the central atom, so oxygen will also adopt an sp2 hybridization in formaldehyde. Now let's redraw the molecules showing the hybridized atomic orbitals, the hydrogen 1s orbitals, and their overlap. How many sigma bonding MOs are being depicted in this sigma framework? These 3 overlaps are all going to produce sigma bonding MOs and sigma anti-bonding MOs, though we'll continue to ignore the anti-bonding orbitals. But wait, what are these 2 orbitals doing? They aren't overlapping with anything. These are not bonding. Bonding orbitals are the result of constructive interference and get bigger in size. They're not anti-bonding. Anti-bonding orbitals are the result of destructive interference. So what are they? They're a new type of orbital, non-bonding. Sigma non-bonding, to be specific. Non-bonding electrons are not shared between nuclei. They're what Lewis called lone pair electrons. What is the maximum number of electrons that can be accounted for in this sigma framework? There are 6 sigma bonding electrons in H2CO, and 4 sigma non-bonding electrons. But wait, What about the last two electrons? We're out of sigma framework orbitals, and we've promised you that you can ignore the antibonding orbitals. What's left? We forgot about the leftover unhybridized p orbitals on the carbon and oxygen. How many p orbitals are left unhybridized in this molecule? H2CO has two unhybridized p orbitals, one on the oxygen and one on the carbon. As we know, if an atom hybridizes sp2, like in the case of our carbon and oxygen, the last valence p orbital remains unchanged. Let's rotate the molecule and take a closer look. Let's see what that will look like. If we draw this molecule horizontally, with the hydrogens and lone pairs perpendicular to the screen, the unhybridized p orbitals will go on the carbon and the oxygen vertically. There, we've seen this before. What molecular orbitals result from two p orbitals on adjacent atoms that overlap like this? That's right, the two p orbitals overlap to make a pi bonding MO and a pi star antibonding MO, just like in the diatomic molecules. This is our pi framework, so the last two electrons will be pi bonding electrons. Just like that, we have our MOs for formaldehyde.